University in Cairo. So I'm glad to be here as an invitation from Sensei to give some lectures at埼玉University. Maybe this is the complement of this first lecture, which was 2 days ago on the CMS tracking system. And today I will give some more information about CERN experiments, not in details that I know that maybe not most of you are specialists in the field, so I'll give just brief notes, and maybe this will be but first I would like to know who is the audience to adjust the level of my talk. So could you please introduce yourself and your specialists? Which grade? Please introduce yourself.
自己紹介を。何でも。
お名前は？健太さんです。There are students here. First, second, third, fourth. First. Which department? Physics, chemistry, biology, physics. Great, okay. Please.
My name is Yuta.
Yuta-san.
I study mathematics.
Mathematics, yes. So which grade? Which grade?
First.
First. Nice to meet you.
Nice to meet you.
So I graduated 9 years ago from埼玉University. I got my PhD from here under the supervision of Professor Helwan in the field of cosmic ray. So the field of cosmic ray may be the link between space energy, space physics and high energy particle physics. So this is why my lectures will be a mix from astronomy and astroparticle physics and high energy particle physics. So this could be a mixture of this field, and that is what we are doing in the cosmic ray actually. So I will start with introduction about CERN. What's the people in CERN doing? And as I did in my first lecture, and I will continue in the next lectures, that at the end of the lecture I will ask some questions. So if you answered it, so you will get a gift. Okay? So I will just show you the gift to encourage you to wake up and answer my questions. What is this gift? Yes. This is a gift. You know what is this? You know this paper? Cover? Barbie paper? These some planets growing in the Nile River in Egypt, and the ancient Egyptian was using it to write. And this is the telegraphic language, the symbols. So each symbol showing a specific character, so you can write your name in such symbol. So this is a gift if you answered my question. So please concentrate on my talk, and I will start with this brief introduction about CERN. So you know what's CERN? CERN pronounced the Central European Research for Nuclear Physics, and just now they changed the name to be particle physics. CERN actually located on the border between Geneva and between Switzerland and France actually, and it is including the largest hadron collider all over the world. So with the LHC, or the Large Hadron Collider, the proton-proton collide each to each other and with energy 10 to 7 tera electron volt. Tera means 10 to 12 electron volt. So they collide proton-proton collisions, and the protons are accelerated in such circular accelerator. The radius of this circle is 25 kilometers. So very huge accelerator, and the proton can reach the energy 14, 10 to 12 electron volts. So this huge energy can produce such strange particles that we will talk about later. So, why we are doing that? Why we spend all this money to make such collisions? Actually, CERN wants to answer mainly two questions. The first question is the Higgs exists or not. Higgs is a strange particle. We consider that it could be the fundamental particle of the matter, and if it will be exists, so we can see it in CERN, because it needs such huge energy to be produced. So the first question we want to answer, if the Higgs exists or not. Then the second question is the dark matter, because with such a huge energy to 14 to 10, 12 electron volts, we can detect some dark matter particles inside some experiments in CMS and others experiments. So, do you have information about dark matter? So, so in the universe, we are only living on 4% of the 100% of the universe, and the others, 96% of the universe is invisible. We call it dark matter. How we know about that such dark matter exists? So if you calculated the velocity of the galaxies around the universe and compared it with each masses, so you will find out that this velocity is not comparable with the masses of these particles. It is very, very slow. After calculations, we found out that there is a 96% of the universe is not visible, but it should be exists. So this is what we call it dark matter. Okay. So again, we have two mainly questions we want to answer to try to find out the dark matter, to try to find the Higgs particle. Higgs particle, some people call it the God particle. So it should be the fundamental particle of the matter. So you know that this matter consists of molecules, and molecules consists of atoms, and atoms consists of nucleus and electron, and the nucleus consists of proton and the neutrons, and the proton and the neutrons consists of quarks, and quarks consists of what we are trying to know right now. So if this fundamental particle exists, so it will be the fundamental particle of the matter, and again its name is Higgs particle. So again we accelerate particles in the LHC with the energy 70 eV, and they collide inside the experiments. We have mainly 4 experiments at CERN: ALICE, CMS, LHC, and ATLAS. This is the main 4 experiments in CERN that these particles collide inside the detector cell. So in the past, or even in the experimental lab of the nuclear physics lab or radio physics lab, so you was putting some Geiger counter detector, and the particle from a radioactive source collide with the matter and be detected by this detector or Geiger counter. So this concept is completely changed when you have such a huge experiment So the collision happens inside the detector itself. Okay. So again, we have four main experiments. So the LHC, the Large Hadron Colliders, consists of the beam screen here. So we are focusing the path of the protons inside the beam with the magnetic field mirrors. So we need a supermagnet to confine the protons inside such large hadron collider. And you know that the supermagnets should be cooled with liquid nitrogen. If you are following the news, 4 or 5 years ago, there was an accident at CERN, and this accident happened that such tubes moving the liquid nitrogen to the LHC, one of these tubes have been broken. So the coils of the LHC was burned, and there was this leads to the stopping of the experiments for maybe 2 or 3 months. So you should circulate cooling the magnets, the supermagnets, with the liquid nitrogen, and this is a construction of the LHC. So the protons going there and moving many times, getting final energy of 40 eV, proton collision, and finally they crashed to secondary particles with energy, the summation of such two energies. So at this moment we reach it to this energy 4 TeV, but in the next year, so we will increase the energy of the LHC step by step until we reach the maximum energy, which is 8 TeV next year. So such pulse of protons, we called it bunches. Okay, so we have maybe 3,000 bunches every second, and the bunch, only one bunch, including 10 to 11 protons. So again, you have 2,800 bunches, each bunch including 10 to 11 protons collide each second. So what you will get? You will get a cascading like we are calling in the cosmic ray. So you're having something like that. So this is a real event, simulation of real event run, and this is the run number. So you could imagine how many events you will get every second. So if you store this data in 1 second for only one run, it will be around 300 gigabytes per second. 300 gigabytes per second. So just a simple calculation. If you recorded this data on a DVD for 10 years, okay, so it will reach the distance between the Earth and the Moon. So this means that this amount of data is very, very huge. So we couldn't analyze such kind of data with our personal computers or even supercomputers. We need a new technology which is called the great technology. And actually I recommend埼玉University here to have a great node, because to run the simulations of such programs, to analyze such kind of data, you should have a great node. You will not be able to do it with your personal computer or even a supercomputer. So this is just showing how many mainframes we have. Just when I visited CERN last time, several weeks ago, I visited this place. It was including 40,000 supercomputers. 40,000 supercomputers. So every month they update and the systems and include additional computers, what we call it tier 0. And again, if you want to log into this tier 0, you should log in from a grid node. You will not be allowed to log in through your computer. So you should have such grid node, and from this grid node we call it tier 3. From tier 3 you are logging to tier 1 in Geneva, and from tier 1 to tier 0, etc. So you are just analyzing the data. While you are sitting here in埼玉University, you are using your computer, logging from your tier to tier 0 in Geneva, and making the analysis, making the simulation, and that's all. So this is a very fantastic system, and a lot of technology is included here. So again, I will return back to my. So I was talking about the LHC, and this is a collision what happens, and such a huge number of events. So what we have as such experiments, this is the first experiment. This is Atlas, around 15 tons of matter. So you can imagine this is a man sitting here. How this detector is very huge. So we have a solenoid in the center. This is concentrating the beam again. So this is the inner detector, hadronic calorimeter, indicators, neon detectors, and barrel. The Alice experiment actually is very huge detector, but we compressed it and mainly searching for the muons in another experiment, which is called CMS experiment. It's the second experiment. Actually, Japan is not included in such experiment. This experiment right now, I encourage also again埼玉University to push the people to participate in this experiment. CERN, especially that Japan is one of the associate members in CERN. So this is the different kinds of the detectors in details. So this is the hadronic calorimeter here. This is the superconducting coil again. This is the silicon tracker system to track the electromagnetic waves, electromagnetic particles like electron. And this is the muon barrel and in the cap. Actually, the Egyptian team is participating in such part of the muon in the caps with a specific detector called resistive plated chamber. This is the construction of the CMS experiment actually, and I will just show you a small film about such construction. Just takes 5 or 7 minutes, something like that. So.
The CMS experiment is located near the village of Cessy in France, about 15 kilometers from the Geneva airport. The complete detector will be assembled and tested in a surface form over a period of about 4 years, starting in 2000. sliding on air cushions mounted under the supporting feet. At a later stage, muon chambers will be inserted between the ring's layers. There are 5 of these rings that support the central part of CMS, called the barrel. The central ring has a special role as it supports the solenoid magnet and all of the barrel detectors. This includes the hadron calorimeter, known as HCal, seen here being constructed in wedges. These are made from brass, interleaved with plastic scintillators. Before inserting the HCal, we will construct the solenoid magnet and put it in place. The solenoid magnet is made of 5 cylindrical sections, which are enclosed within outer and inner vacuum tanks. The magnetic field supplied by the solenoid is 4 Tesla, about 100,000 times that of the Earth. At this point, the HCal is inserted into the solenoid and will be followed by the electromagnetic calorimeter and the uretrometer. The CMS detector is completed by 2 end caps, which contain muon chambers and also support calorimeters. Each end cap is made of 3 layers of steel that form the end cap return yoke, similar to the barrel, assembled in wedges. The layers are joined together, separated by steel rings. The front layer supports the end cap calorimeters. The end cap hadron calorimeter is assembled in wedges on a circular support plate. Its structure is similar to that of the barrel HCal. The end cap HCal is rotated and lifted into position on the front layer of the return yoke. This will be followed by the addition of the end cap electromagnetic calorimeter in front of the HCal and the insertion of muon chambers between the steel layers. The 5 barrel rings and the 2 end caps fit together to form the compact muon solid, which will be later lowered in segments into the underground experimental cavern.
Well, this is the construction of the CMS experiment. And now we tracking the particles inside. So we have several detectors. Each detector is giving a signal to a specific kind of particle. You know that there is no universal detector. each detector can detect specific kind of particles within specific energy. So we have several kind of detectors in such experiment. Actually, the tracking of the system for example, for the photons, we use silicon crystals that making emission when the photon collide with it. So we collect the signals with photomultipliers, and this is used for detection of the photon. For the neutron, we use for the neutron and the proton. Actually, we use the electromagnetic calorimeter. For the muons and maybe neutrino, we use hadronic calorimeter at the end of the experiment because they have a very high penetration. So this is the construction of the tracking system, and again that's what we have in when you collide such a proton-proton bunches. So to find the Higgs, we are searching actually within all this data in the signature of the resonance of two muons or two electrons. So you could imagine how this will be very difficult. You have such amount of data and you are searching for a single event with such signatures. So this is not easy at all. If this signal is found, resonance of two protons, resonance of two electrons or two muons, so this means that the Higgs particle have been created. And right now we detected some signals, the CMS, it's around 5 or 6 signals, but such low statistics is not convenient for the scientists to say that, okay guys, we got the Higgs particle, but when we assure that, of course the one who will assure it will get the Nobel Prize. So,
is that a simulation result?
No, this is
the experimental result?
No, this is the experimental result, yes. This is the experimental result. The last one. So, we found some signatures for the Higgs, but again, the statistics is not very high, so we couldn't measure. And also that happened in Alice experiment. So Alice and CMS are competing each other, and everyone wants to get the signals first, and they also detected some events for the Higgs. Finally, the update or upgrade of the CMS experiment will depend on inserting some new detectors at the epicaps with high angles of eta. So this detector actually called GEM detector, and I talked in brief about GEM detector in my first experiment. Just I will include only one slide of that lecture 2 days ago. So the GEM detector depends on installing the thin surface of copper with small holes inside, and you have several layers of such GEM strips. And what's this GEM strips doing? Actually, they are modifying the electric field and guide the secondary electrons to localize in such small spaces. So they are localizing the electric field like this, at the bottom. So the electrons, when they come here and producing secondary electrons, so they are confined within this area and be detected in this strip. So the advantage of this detector is that you can define the position or the location of the interacting particle. So, for example, when you have Geiger counter, if this is a Geiger counter, if the particle is coming here, so you will detect it, but you don't know if it is coming from here or here or here or here. So, but in the GEM detector, so if the particle is hitting here, so you will find the signal from this strip. If the particle is hitting here, so you will get signal from this strip. So you can define the location of the particles. This is the advantage of the GEM detector. And finally, have a proposal for a joint project with埼玉University, including the assembling and testing of the gem detector, and maybe as a complement of this project that we can produce the gas photomultiplier from gem detector. Actually, as I noticed that you are maybe not a specialist, I didn't go in details about the particle physics and standard model. I was including them in my talk, but I will not talk about them because maybe this will not be proper. So again, I'm very happy that I am with you here in埼玉University after 9 years ago, and I wish that you can continue your research in that interesting field. Actually,埼玉University is one of the leading universities in Japan, and I think Professor Inoue can include such activities within the highest project, or even as another kind of joint projects. Thank you very much. And I will start my questions.